All right, today during the lecture time, we're going to review for our first exam, which we're still on the schedule. Should be next Tuesday. No, Thursday. This is Tuesday. Thursday, we'll have our first exam, and that's the only activity we have on Thursday. Just the exam. Got the whole class period to finish that. Unless you make other arrangements. We're going to work from the review document, and notice I've got some of them highlighted. That's just so I don't wander. I picked out ones that are representative of the multitude of questions you had to work with. A total of 205 points. So there's not going to be that much on the exam. I've had that question before. No, this is to give you practice. So I've picked out ones that are representative and these types of questions you can expect on the exam. If you don't think of anything you're having trouble with now and something pops into your head while we're in process of doing these, interrupt me, because I want to get your problems fixed first before I just throw out this other stuff. You can see what I'm doing now is, or after when I get started, is just filling time. And hopefully it'll trigger something in the back of your mind that you may have let slip and you want to talk about. So stop me if that's the case. All right. Otherwise, let's see. I've got these blocked off into groups for chapter 1 and chapter 2. So we're going to do chapter 1 groups first and start off with number 1. So, and this is the format of an exam. Mostly multiple choice. You'll have some fill in the blank and some, I wouldn't call them discussion questions. When we get to the point where we're doing chemical reactions and things, you may have to write out the whole reaction. But largely, they're multiple choice questions so that I can grade them quickly. Because I want, when you come in here to take the exam, I don't want you to leave the room until I've graded it. So you know right away where your weak spots are and you can deal with them before the next subject comes to haunt you. Okay, number 1. Which of the following is an example of a quantitative observation? The difference between quantitative and qualitative. That's what we're trying to impress here. Qualitative. Right. When you see quantitative, think numbers. Yeah, quantities. So if we look down a test taking technique, when you got presented with a multiple choice answers, try to work as quickly as possible. The multiple choice is going to give you choices, and some of them may be the answer that you get if you work the problem wrong. Okay, that's how sneaky we can be. So you need to be sure that you work the problem correctly so that you can find the correct answer. And then there are also answers that may be 2 of the above, none of the above, all of the above, that type, those are wonky ones. And they may be D and E, for instance. So really you only have to look at A, B, and C to find out which ones are true or which ones fit the question. In this case, which of the following are quantitative observations? You look at A, piece of metal is longer than the piece of wood. That's qualitative. There's no absolute numbers there. Solution 1 is darker than 2. That's qualitative again. 3, the liquid in beaker A is blue. We're still qualitative. D, the temperature of the liquid is 60 degrees. That's it. That's a number. And then you look at E, at least 2 of the above. Well, we only found 1, so E can't be that. Right. So you try to work as fast and efficiently as possible when you're taking an exam. That's D. D would be the answer there. Okay. I'm going to try to speed things up. Rolling into it slowly and gradually pick up steam. And they should become more challenging as we go, actually. Okay, 2, generally observed behavior that can be formulated into a statement, sometimes mathematical in nature, is called. And sometimes it helps to look at the answers to see what the questions are getting at. We have observation, measurement, theory, natural law, experiment. All right. The only one that fits those particular words, that statement, is natural law. Right. Or if we've only referenced it in discussions, in class discussions, as law and not natural law, pick the best answer. And the best answer is natural law. Okay, that's another rule to go by when you've got multiple choice. If your answer is not exactly, say you're off by a hundredth of a point, then it could be just rounding error, and you pick the best answer. When in doubt, pick the best answer. So D should be your answer for number 2, natural law. What's a theory? While we're at it. Okay, laws say how, right? Theories say why. And most theories have models with them. And they could be mathematical models, they could be physical models, they could be models that don't exist in the natural world, right? But they're attempts to put the theory into a shape that can be modified some way. Okay, number 5. Everybody memorize their prefixes. For these 4 metric prefixes, we want to order them from smallest to largest. And what we mean by there, the smallest modification of the base unit to the largest modification. So when we have nano, milli, centi, say nano, milli, centi. I'm going to try to get all of them up here so we can put them in order. Kilo, milli, nanny, centi, kilo, milli, centi. Okay, that's all of them. Yeah, that's all of them. So the smallest of these is what? Well, nano prefix means times 10 to the minus 9th. Right? Milli is 10 to the minus 3rd. Centi is 10 to the minus 2. Kilo is 10 to the 3rd. Right? They're already in order. Here's your answer. Okay. Couldn't be simpler. Let's see. Which ones did we leave out? We left out deci, right? 10 to the minus 1. Oops. 1. Let's see. We got down to nano. How about 10 to the minus 12? That's a pico. Okay. We're not going to go any smaller than that. Oh, we didn't go bigger. How about 10 to the 6th times? Instead of a little m, that's a big M. Mega. Okay. Let's see. I'm thinking in terms of computers. We used to have megabyte was big. It's tiny now. Megabyte, what's bigger than mega? Yeah, I skipped one. Gigabyte. 10 to the 9th is gigabyte. Well, if we put a byte behind it. And 10 to the 12th is the one you're at. Terabyte. Yep. That's a standard size drive now. External or internal hard drives are in the terabyte range. In fact, I think this one right here is a solid state drive that goes up to 4 terabytes. I got another one that's a mechanical drive. I think it's 4 or 5 terabytes. You have to be very, very careful with these guys. They can only stand so many G's of shock. And I've ruined a couple of them. Just slipping out of my hands, smacking the floor. They're lead weights by then. Okay, enough of that. That's number 5. Let's see, let's go to 6. unit conversions. When you have a unit conversion problem, you look at what you got, kilograms, and what the problem says you need, grams. Then you need a conversion factor, one or more. Right? We could have a chained conversion. In this case, we're in the same system, metric system, and SI units, and all we have to do is use one conversion factor so that numerator, denominator, the kilograms cancel, and leaves us with grams in the numerator. So this one, if you have a chain, eventually you're going to get down here in the numerator that's the same unit as that one. We only need one in this case. So you can do it two different ways. You can say how many grams are in a kilogram. There are 1,000 grams, right? So you can say 10 to the third grams per 1 kilogram. Or actually, that's the best way to do it. And if you look at it this way, this K, this kilo, is the same as that. Okay. So 8.1 times 10 to the third, 10 to the third grams, which is B. Okay. The reason I give you a whole lot of these problems is so that you'll get bored working. I want you to be bored working these problems, because if you're bored, then you know them pretty well. Convert 0.3980. Yeah. 0.89. Is that right? No, my dyslexia is kicking in. 389. 0. Meters to millimeters. Okay. Now, there are two approaches. Once you get comfortable with these, you can move quickly. And you can say, all right, if the unit's going to get smaller, the number needs to get bigger. So that tells us which way the decimal moves. If we need to get a bigger number for that one, then the decimal has to move that way. And we know that milli is 10 to the minus third of a meter. So we've got to move it 1, 2, 3 places right here. So we should have 389.0 millimeters. Or you can go through the unit conversion process and say meters here, millimeters there. And we know that this is 10 to the minus third meters is 1 millimeter, because milli means 10 to the minus third. And if you divide by 10 to the minus third, it's the same thing as multiplying by 10 to the third. Right? Move it into the numerator, you just change the sign. And 10 to the third times this moves the decimal over here and get the same number. And of course, we had 4 significant figures here, we have 4 here, which is A. Okay? Am I talking too fast? Okay. All righty. We're getting those unit conversions under our belt. 9, what's the measure of resistance? 9. This may be stated a little bit differently than we did in class. What's the measure of resistance of an object has to a change in its state of motion? This references Newton's first law of motion, right? An object, anybody in here have physics? Physical science? No? Okay. Newton's first law of motion says an object in motion tends to remain in motion unless acted upon by an external force. Or an object at rest tends to stay at rest unless acted upon by an external force. And the law works because of mass. Every mass resists change to its current condition. So what's the measure of resistance of an object has to its change in motion is mass. Okay. Let's see. Still see it up there. All right, number 11. As part of the calibration of a new laboratory balance, a 1 gram mass is weighed with the following results. What we're implying here is at the 1 gram mass is the standard. That's the accepted value for the mass. So if it's accepted at that mass, and we measure it 3 times, and we get 1.201, 1.202, 1.200, plus or minus, each is the same, yes, 0.001. We didn't talk about plus or minus things. 0.001. What we're claiming with this plus or minus is the accuracy of the measurement. So the accuracy of the measurement is within 1,000th, plus or minus 1,000. So it could be, in this case, it could be what? 0.200 or 0.202. That's what we're claiming. This one could be 203 or 201. And this one could be 201 or 199. Okay. So the question is accuracy and precision. So are these values accurate compared to the accepted value? No, none of them are. So this is not accurate. How about the spread of values? Are they close to each other? Yeah, because they're plus or minus 0.001, and the average there of these values is 1.201 plus or minus 0.001, which means they're pretty close together, which means they're not accurate, but they are precise. Okay. This is also known, goes by another name. We didn't talk about it yet. Systematic error. It's a predictable error. It's off by just a little bit, and we know which direction it is. Well, actually, I might be stretching the truth here. We know that it's within this amount. Systematic error typically is we know how much it's off exactly every time. So if you have a grouping like this, then you can claim it's systematic, because you would have, it's like your bullseye. It's here, and you got right, those measurements there. All you have to do to correct it is to just, move your gun sight, and then you're on target. The other is random error. That's the one that's the real bugaboo in research, because you don't know what's causing random error. You can speculate, but the only way to handle it is, well, actually there's several ways. One, the most often used way to handle random error is just make large numbers of repetitive measurements. Okay. And you take the average as the true value. Systematic error is usually due to an instrument malfunction or an instrument inaccuracy. It's always one direction by a certain amount. Or you have an operator, a technician, that always makes the same mistake every time. And that happens more often than you would like to think. Anyway, not accurate, precise would be C. Okay. Oh, and with our targets, let's see. 12, 13, and 14 probably are referencing our targets. Before we get off the error discussion. Let's see, 12, 13, 14 for sure. Do we got 15 also? No, just 12 and 13. Not doing 14 yet. All right, 12 says, which of the following figures, have high precision? Well, high precision means tight grouping, right? So Roman numeral 2 and Roman numeral 3 fit that bill. So 2 and 3 is E. Okay. Let's see, 13 says, which of the following figure 1 represents system. Okay, here we have systematic and random error. All right. Like I said before, systematic error shows the same type of error every time. So the ones that are off target and grouped tightly, showing they have the same error each time. So 2 and 3 are systematic error, and 1 is random error. It's all over the place. There's no rhyme or reason to it. So it looks like B, figure 1 represents random, figure 2 represents systematic. Oh, excuse me. 3 doesn't represent error, right? Because it's on target. Okay, my mistake. All right, let's move down to 16. The amount of uncertainty in a measured quantity is determined by what? We kind of alluded to that already. The instrument, the limitations of the measuring instrument, right? And usually the more accurate the instrument, the more it costs. And it goes up exponentially. I used to have an instrument. I used elemental analysis of plant materials and soil extracts. It's called the inductively coupled argon plasma spectrometer, which is a mouthful, and it costs $250,000. So, you know, that's a drop in the bucket to the government. But it was extremely accurate and could analyze a single sample for multiple elements, concentrations like that. But it had to be maintained properly. Right? You had to have regular service on it. You had to, and then the second part, you had to have an operator that knew what they were doing. So I learned how to use it and get good results. And then I trained my lab assistant to use it, and then I could go off and do something else. And she was very good at it. In fact, she was better at it than I was. So, 2 factors that determine the accuracy of a calculation is the operator and the instrument, which is A. Let's see, 17. A scientist obtains the number 04500 04500 700 700. Okay. On the calculator. If this number actually has 4 significant figures, how should we write it? Well, remember, that's significant. Those 3 are significant, right? Non-zero numbers. Captive zeros are significant. Leading zeros are not. And trailing zeros are significant if you have an explicit decimal point. So these are significant also. But we're only supposed to have 4, correct? So we start with the left-hand most significant right here. 1, 2, 3, 4. So we have to draw the line there. This one's greater than 5? Yes. Huh? 6.
Yeah, he missed the 6.
Oh, sorry. Thank you. I'll leave that in the video. Just shows you I'm human. Okay, so significant, all those are significant, but we're only allowed to keep 4 of them. So now we go 1, 2, 3, 4 right here. That's greater than 5. So we have 0.04501. That's where you stop, which would be E. Right, and just for argument's sake, what's that called? That's an orphan decimal. They're not permitted in this class. Okay. Okay, let's see. Let's keep scrolling until I find another highlighted one. There we go. Express this number in scientific notation. 0810. 0.0810. Did that right? Yeah. Okay, so scientific notation requires that the coefficient is between 1 and 10. And that means we have to move the decimal to the right 2 places. We keep that 0 because it's significant. And then we store up the movement here. 1, 2 to the right is negative. -2. Okay. And that should be B. That was 2021. Let's see, express the number 6.49 times 10 to the -3rd in common decimal form, standard format. 6.49 times 10 to the -3rd, is it? Yeah, okay. This is negative movement of the decimal. It has to go this way. 3 places. So let's stick some zeros out here so we have a place to move. 1, 2, 3, right here. We don't need that one. And rid of that. So we should have 00649. And that's still only 3 significant figures that we gathered from the scientific notation. See, the answer is A. Yeah, A. Okay, 22. Express this number in common decimal form. All right, so we're going to go the other way. 10 to the 4th one. Yeah. So now we need to make, this is 10,000. 10 to the 4th is 10,000. 10,000 times this moves the decimal to the right. Makes the number bigger. So 2, 3, 7. Let's see, we need some zeros over here. 1, 2, 3, 4. And since that's not significant, actually, it's understood 0. We can't put a decimal there because if we do that, it says 5 significant figures, and we've only got 3. So if we do that, that gives 1, 2, 3, and those are not significant. Okay. All right, 23. We generally report a measurement by recording all the certain digits plus how many uncertain digits? Always just 1, right? It's the furthest one to the right. All right, 24. You're asked to determine the perimeter of a cover of your notebook. You measure the length is 39.36. Let's see, let's draw a picture. 39.36. What is it? Centimeters. Okay. And the width is 24.83. Okay. Now, how many significant figures should you report for the perimeter? What's the perimeter? Added this one. It's also over here. This one, it's also up there. So you got 4 numbers that have to be added together. All right. And to find out the number of significant figures, can we just look at that and say, oh, there's going to be 4 in the answer? No. This is an add subtract rule. Right. Multiply, divide, yes, you could do that. If we had area, so how many significant figures in the area? 4. Right. But not in the perimeter. You have to add them together, lining up the decimals. There we go. So we can keep everything down to that decimal place, down to the hundreds, because they've all got hundreds places. So if we add them all up, let's see if I can do that. See, 6, 18, carry the 1, and that's 6, 7, 15, 23. Carry the 2, 11, 20, 28. Carry the 2, 2, 4, 6, and 6 is 12, right? 5 significant figures in the answer. Okay. Simply because it's a different rule. I know if you get in a hurry on an exam and you're not careful, you could slip into that add, subtract, you could slip into the multiply, divide rule where you should be using the add, subtract rule. Okay. Consider the numbers 23.68 and 4.12. Right? I extract information from word problems because word problems have their primary purpose is to confuse. So if you extract the information from the word problem and then look for the question, you're less likely to miss the mark. The sum of these numbers has how many significant figures, and the product of these numbers? Okay. The product is easy. The product is 3. The sum, that what it says? Sum, yeah. The sum, these are lined up like that. So that's 10, 7, 8, 7, and 2. Right? Is that right? 10, 8, 2. That has 4 significant figures. Okay. So the answer should be 4 and 3. D. All right. Here we've got a combination. Oh, that's not highlighted. Okay. You know what to do with a combination. PEMDAS. Parentheses first. Good. We got parentheses in that number. So you add those two together. How many significant figures does that give you? And then you divide by 5.10 and check your multiply divide limits. Okay. Should end up with 2 significant figures. And I suspect 2 significant figures only because that add subtract limits you to the decimal point. You've only got the 2 on the left. Do it in your spare time and see if I'm right. All right, 27. Using the rules of significant figures, calculate the following. Okay. So here we've got a subtract rule. And 179. 179. Okay. We're going to be limited to this position. But we're not going to do anything with it until we have to round it. So 0 from that's 1. And that's 3. That's 2. 9 is 8. And we have 3 left over. So we have to limit here. That means 3.823. And we don't put a 0 placeholder out there because we've got that decimal. And we can't say that that's significant. So it just drops off. And we keep it at 3.823. Okay. All righty then. Here's a complicated one. We try to make them look complicated, but that's to hopefully force you to be very methodical about your procedures. More complicated a problem gets, the more your skills at breaking problems into smaller pieces becomes. In this case, we have, let's see, 32. In this case, we have 3.478 times 1.164 grams divided by 2 milliliters. Okay, the parentheses. Oh, and then we got a minus 169, 0.169 grams per milliliter. Okay, so the question asks us for the actual answer. All right. This is going to be, that's a dimensionless times G is going to be grams per milliliter. This is grams per milliliter. So we can subtract them because they're apples and apples. Right? If they have different units of measure and we try to subtract them, that'd be cheating. If they don't have the same units of measure, you can't compare them in any way. All right. So if we do that first part, we have to do this one first and then apply the, let's see, let me be sure. Yeah, add, subtract is last. So we do all of this first. And then do the subtract. In my calculator. Is everybody on the calculator now? Okay. And 3.478 times 1.164 is that number, and then we're divided by 2. Okay. And this gives us, my calculator says, for this part right here, says 2.024196. Okay. The add subtract rule has to be, the multiply divide rule has to be imposed before you can do the subtract. So we're limited to 3 significant figures. Right here, that means 4 is less than 5. We have 2.02 minus 0.169. Okay. Now we're limited to that place. And these are both grams per milliliter. So 9 from 10 is 1. 6 from 11 is 5. And 1 from 9 is 8. 1.851. And we round it off. That's 1, so we just dropped it off. 1.85 grams per milliliter. Okay.
You mentioned it. How did you divide the grams by the milliliter? So
well, the product of this one is going to be grams because that one has no dimensions.
right.
So anytime you do something to the number, you have to do the same thing to the units. That means this is in the numerator, that's in the denominator, and that becomes grams per milliliter.
Okay.
Yep. That was already given, but this one comes from the calculation. Right? Okay. Is anybody having trouble with math? You okay with the math? Okay. Because I have a little quiz that I sometimes give the class if there's any question about your math skills, and it gets harder and harder and harder as you go. And I give you maybe 10 minutes to do it. And how far do you go? And beyond that is no man's land. Right? So those are the ones you need to work on. So if you want to, I can give you a copy and you can test yourself. But I thought in the interest of time, skipped over that part this semester. Express the volume 781.2 cubic centimeters in liters. 781.2 cubic centimeters, and we want liters. Okay. What's a cubic centimeter equal to? Remember? Maybe that just kind of flew over your head when we discussed it in class. Cubic centimeter is equal to a milliliter. Exactly the same. So when you give, when you're ordered to give somebody an injection of 10 cc's of blah, 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 you're actually giving them 10 milliliters. Okay, so now that we know that, we're in volume units. Well, both are volume, but this is usually reserved to solids. But since we're headed for liters, I figured, why don't we convert to milliliters first? That makes the conversion simpler. Milliliters is in the numerator. So the denominator here cancels them, leaves us with liters, and we have, well, why don't we do it this way so we don't have to move? 1 milliliter is 1,000th of a liter. Okay. So we have 781.2 times 10 to the minus third liters. And then we want to convert that to what? Standard notation. Okay. Can do that. If we want to combine this into that, we have to make this one smaller to take advantage of that 1,000th of. Move it 3 places. So 1, 2, 3. 0.7812 liters. And we can keep all of these significant figures because we didn't introduce any other variables. They're all there, which would be T. Okay. And you can use unit conversion techniques if you want. That's fine. Just takes a little longer. If you have very complex calculations, sometimes unit conversion techniques are probably more reliable than moving decimals. Because I've seen students move the decimal the wrong direction. And the answer is probably there, right? Because we anticipate those types of errors and put that answer in the selections. Okay, 37. The pressure of the Earth's atmosphere at sea level is 14.7 pounds per square inch. Okay, that's pressure. We're going to talk about pressure in more detail later. So just accept it as is. It's a force per unit area. Okay, what's the pressure when expressed in grams per square meter? So we're headed for this one. Grams per square meter. All right, when you have a conversion that has multiple units in it, pounds and square inches, just do one at a time. It's all going to be multiply, multiply, multiply. So just pick one. I'm going to do pounds first. We want to end up with grams. So we've got to not only change the size of the unit, but the system that it's in. And it looks like we have conversion factors given to us. 2.205 pounds per kilogram. So I can convert pounds to kilograms. 2.205. Okay. Now I can go to grams because I'm in the metric system. Kilo means 1,000. Okay, I'm gonna need more room here. We're going to grams per square meter. Kilograms. I want to go to grams. Notice that where I'm headed is always in the numerator. And I'm canceling what's in the denominator for my next conversion factor. So this is 1,000 grams in a kilogram. Now we've got grams done. Next, we want to do square inches to square meters. We got to change system again and size. So we're given 2.54 centimeters equals 1 inch. So if we cancel the inches, now the inches have to be up here. I said where you're headed is in the numerator. That's if there's only one unit. If it got a unit in the denominator, you want to end up with that unit in the denominator. So we have this 2.54 centimeters per 1 inch. But what's wrong with this picture? The conversion factor is linear, and the unit we're trying to convert is area squared. Here's the way you do that. You want to get square inches? Square the whole thing. It squares that and that. Plus, you got to square this one too. That solves the problem. So this square inches now is canceled by that square, but this still has to be squared. Okay, when you do your calculations. Now that we have square centimeters, we want to go centimeters to meters. So centimeters has to be up here, meters down here, and we know that we have 100 centimeters in a meter, but we're stuck again because that needs to be squared. There you go. So we're going to square this, we're going to square that, we're going to square that, we're going to square this in order to cancel this one. So we're going to square this one, square that one, square that one. Okay, now we've got grams and square meters, just what we wanted. That's the brainy part, the thinking part. The rest is just number crunching. So 14.7, and the way I do it in my calculator is I just go all the way across numerators and then come back and divide by the rest. Okay. If you've got an algebraic calculator, you may have to insert parentheses to get there, or do individual equals and then times and equals and times and equals and divide by equals. That type of thing is tedious. With a reverse Polish notation, you can do it a lot quicker. Anyway, 14.7 and then 1,000 times that, and then 10 to the fourth, right? 10,000. times. Now we go back, 2.205 divided into that. 2.54 squared. Squared, divide that in, and then that's it. 1 squared is 1. And I get, let's see, these are all exact numbers. Conversion factors are always exact, so they have an infinite number of significant figures. This is the only one that limits, and this is all multiply, divide. So 3 significant figures out of this number, 1.0333333 times 10 to the 7th grams per square meter. I can only keep 3 of those, so I have to cut it off right here. 1.03 times 10 to the 7th. Should be B. Okay. It looks like a huge problem, but we broke it down into pieces. We do that one first. Get it done. Then we do this one next. Get it done. Use a trick or two. And then once you've done all the thinking, then you can pull out your calculator. All right. 37. We do it. Use 45 minutes already. Only got a half hour left, right? I'm probably not going to make it. Fortunately, our lab won't take a whole lot of time because you're not going to finish it today. We're going to introduce it, and then it's not due till the next time we actually go in to do a lab. So that means the lab we're going to introduce today is not due until February 11th. We won't have lab next Tuesday. We save you a trip. Right. So you have all that time to finish the first lab. And it's not, we're not actually going to walk in there and do the lab. This first one and second one, lab techniques, those are informal labs. I've said this before, but I'll say it again. So you don't need a notebook entry to do these labs. I'm giving you time to get all your stuff together, like get a lab coat, you know, get glasses if you want them, safety glasses. Get yourself a notebook. Everybody got a notebook? And you know how to set it up, right? The first inspection, I'm just going to be looking for cover, identification, table of contents, every page numbered. Right hand side odd, left hand side even. Okay. That's all I'm looking for the first time I inspect. Which is when, while I'm on the topic. First inspection, I'm going to do. Here it is. February 11th. So when you turn in your graphic techniques, I'll look at your notebooks too, and just see if they're set up. Next time I inspect them will be when we want to go in for 18th of February, when we go in for waters of constitution and hydration. That's a formula. So I want your notebooks, the lab method set up properly. Okay. So that I know that you know what you're doing. You're not going to be a safety hazard. Okay, back to the topics here. Let's see, we already do that one? No, we didn't. Density of liquid mercury is 13.6 grams per mil. Density of mercury, 13.6 grams per milliliter. Okay. What's the density in pounds per square inch? Okay, this is another multiple units of measure conversion. Right. So 13 grams per milliliter. And we want to end up with pounds per cubic inch. Pound per cubic inch. Okay. So which one do you want to do first? Grams or milliliters? I'll let you decide. We did the top first. You want to do the bottom one first this time? Just to be different. Okay. we want to change to cubic inches from milliliters. So what conversion factors are we given? Centimeters to inches. Right, so let's convert that to cubic centimeters. Right, we can do that. Now we can convert centimeters to inches. And what's the ratio? Well, 2.54 centimeters per inch, but they have to be cubed. Okay, that takes care of the denominator, cubic inches. All right, now we're going to do the top. We need to go to pounds. So our conversion factors given are 2.205 pounds per kilogram. Well, we don't have kilograms yet. So we got to get kilograms up here first. 10 to the third grams. Then we can use our conversion factor for kilograms, pounds. 1 kilogram is, no. Yeah, 2.205. 205 pounds per kilogram. That takes care of that one, this one, did that one out. This one's cubed, so we're good to go. Now we just crunch the numbers. 13.6, 2.54, and I'm going to cube it. On my calculator, it doesn't have a cube function, so I have to use an exponential function. So I'm going to enter it, say 3, and get that one there. That one is times. Then 2.205 times, now come back and divide. I only have this one to divide, 1,000. So I end up with 0.4914153 pounds per cubic inch. And I'm limited to 3 significant figures. So we stop right there. 0.491 pounds per cubic inch. Oh, it's in scientific notation. Okay. 4.91 times 10 to the minus 1 pound per cubic inch. That's B. Okay. All right. And 46. In a week. During a physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? Okay. The question is, how fast is that electron moving in miles per hour? Okay. What's the speed of light in a vacuum? In English terms, you remember? Maybe you don't know. 186,000 miles per second. But the electron's not moving that fast. The electron's only 93% of that speed. Or we can use the values given to us, 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. And we're only going to convert 93% of that. The decimal equivalent of 93% is 0.93. Okay. So that's what we want to convert. If we're going miles per hour, then we want to convert one or the other. Let's convert meters to miles. Okay. What are we given here? Kilometers per mile. So let's convert that to kilometers first. Meters. So how many meters in a kilometer? 1,000. Because A means 1,000 times. And then more room. Then we can convert kilometers to miles. Okay. And our conversion factor there is 1 kilometer is 0.6214 miles. 6.2 miles. There we go. Got the miles done. Now we want to do seconds to hours. Yeah, hours. How many seconds in an hour? Seconds up here, hours down here.
3,600.
Yeah, 3,600. 60 times 60. Right, 60 seconds in a minute and 60 minutes in an hour. So that's 60 squared is 3,600. There we go. So that takes care of seconds. And we got hours here and miles there. We're good, miles per hour. So in the interest of time, I'm not going to finish that calculation. It should be 6.2 times 10 to the 8th miles per hour. And that's actually, no, that's not right. It's the best answer out of your choices, but that's only 2 significant figures. And we've got 3 here, don't we? Okay. So I guess that's a lesson. When in doubt, pick the best answer. You know what I think they're doing is they're imposing this 2 significant figures on that answer, but that's an exact number. So it should be 3. Okay, 49. In 1928, 29.3 grams of a new element was isolated from 660 kilograms of the ore molybdenite. One guess what the element was. Molybdenum. The percent by mass of this element in ore was. Okay. So if we got 29.3 grams of the element, 29.3 grams, I'm going to go ahead and call it molybdenum. In 660 kilograms of ore. In 660, only 2 significant figures, kilograms of ore. So its percent by mass is grams per 100 grams. So if we don't have to change this part, it's that many grams. How many grams per 100 grams? If it's 660 kilograms, we just need to convert kilograms to 100 grams, right? Because parts per 100, grams per 100 grams, that's percent. Okay. All right. And if I haven't said it before, percent is a very tricky unit of measure because it's dimensionless. Right? Grams cancel and you're left with parts per 100. So if you don't know the source, then you don't know what it was made from. We're saying it's percent by mass, which means grams per 100 grams. And very often when you see percent, you'll have qualifiers on it. This could be mass, or it could be mass, volume, or it could be volume. Or if you go to the liquor store and buy alcoholic beverage, it'll be ABV, percent alcohol by volume. Okay. That's right. You guys don't read labels, do you? Okay, let's back to the problem. So this should get us where we're going. That will cancel kilograms and leave us with 100 grams. So let's see if I did this right. 29.3 divided by 660 and then also divided by 100 should give us 4.43939 times 10 to the minus 4. These 2 are the only ones that restrict. There are 2 significant figures here, so I'm restricted to 4.4 times 10 to the minus 4. And okay, standard notation. So if I got 4.4 and I move to the left, right? Have to make the number smaller. Left 4 places. 1, 2, 3, 4. So it's 3 zeros and a 44. Oops, that's not right. What did I do wrong? Hold on a second. 29.3. 660 divide 400 divide. Okay. Okay. All right, let me work the problem a different way. What about that? And see if I can find out where my error is. All right, let's take this one now. This was the answer I got from that method. Okay. Let's change our method. How many grams of molybdenum per gram of ore? Okay. So kilograms of ore, gram of ore. We'll do that conversion first. This is 10 to the third per kilogram. Okay. Now to make, that's a fractional value. Grams cancel. It's a fractional amount. Times 100 is percent, right? Okay, I can see where it's going already. 29.3, 660, 1,000 divide 100 times. Okay, now I've got 4.4. Yeah, just leave it there. Times 10 to the minus 3. Okay, that gives me 0.0044. All right. So there's something wrong with my logic here. This is the more reliable form. At least that gives you the answer that's in the key. It should have worked. I don't know why it didn't work. I did something wrong. All right, next problem. Or you could look at it logically. No way it's going to be 44% or 6% or 29 or 19%. So process of elimination, D has to be the answer. Okay, Kelvin to either Fahrenheit or Celsius. So Kelvin equals Celsius plus 273. Or if you want to, 0.15. So we could test it since we've got 2 different units of measure in the answers, and we've got to go to Celsius first before we can get to Fahrenheit. Let's test the Celsius first. So Celsius is going to be K minus 273.15. And if K is 409, we don't even need the 0.15. Then Celsius should be equal to, let's see, 136 degrees C. Right? There it is. So we don't even have to do Fahrenheit. But if we did have to do Fahrenheit, how would we do it? Well, the conversion formula is in useful information, and it'll be on the exam, last pages. I memorized it this way: 9/5 C plus 32. So we just plug 136 in here, calculate F, if we needed to. Or if you're good at algebra and you needed to go to Fahrenheit, you could combine those 2 equations into one. Right? Melting point of a certain element is 391 C. What's the Fahrenheit scale? I'm not going to stop on this one because we're low on time, but you just use that formula. F equals 9/5 or 1.8 times C plus 32. Plug in the C, spits out the Fahrenheit, look for the answer. Let's see. We can do this one. 54. We're not even out of chapter 1 yet. 1984. Okay. This is what's called blue smoke. Word problems are famous for that. They give you a lot of information that you don't need. Right? Who cares if it's 1984? Some drums of uranium hexafluoride were lost in the English Channel. Okay, so what? What's the question? Which is known for its cold water, about 17 degrees C. So the water is 17 degrees C. Okay. Melting point of uranium hexafluoride is 148 F. 148 F. Okay. What's the physical state of uranium hexafluoride in these drums? All right, it's kind of a dumb question because, just think about it. 17 degrees C is only 17 degrees above freezing point. And the ratio of Celsius to Fahrenheit is 1.8. So if it's 17 degrees above freezing, then times 1.8 would be what? Oops, I went the wrong way. 17 times 1.8 is 30.6 degrees Fahrenheit above freezing point of water. So 30.6 degrees above freezing point for Fahrenheit would be 32 plus 30.6 is 62.6 degrees. Right. So it's still solid. That makes sense, or did I run around the barn backwards too many times? Uranium hexafluoride, pure uranium, takes a lot of energy. It has a very high melting point. Right? So when the Manhattan Project was trying to purify uranium and separate the U-235 from the U-238 to make a bomb, the technologies of the day required that it be a gas. Right? Well, they discovered that uranium hexafluoride was a compound that had a lower melting point, a lower boiling point. Right? So they convert uranium into hexafluoride, and you can turn it into a gas with less energy, and then you can put it through your processes. One was a diffusion plant that was probably as big as the city of Beckley. I used to live in Oak Ridge, so I know how big it is. And they just had filter after filter after filter, and they used Graham's law to separate. Right, the lighter one, the 235, would go through the filters quicker, so each step would enrich it further. The other way was, well, now they use ultracentrifuges. Right? It still has to be gas. And then there was one other one, magnetic sector. So you fire these things through a big magnet, and the lighter ones bend more than the heavy ones. So you just bleed them off. Okay, so the answer there is solid. It has to be solid. Okay. This 156 is a little bit tricky. You need to draw a picture to get 56 done. Here we go. Okay, a monolayer. What's a monolayer? One layer, right? It's a layer of, in this case, molecules spread out over ideally a circular shape. It's one molecule thick. These molecules, oleic acid, are oriented in such a way they have two ends to them. One is a hydrophilic end and one's a hydrophobic end. The hydrophilic end dissolves or is attracted to the water. Right? We put a drop of this oleic acid on the surface of the water and it spreads out. As it's oriented its hydrophilic end here, and its hydrophobic end that way is sticking straight up. So there's the water, and there's individual molecules. Okay. That's the way your detergent works on your clothes. It bridges the gap between oily, soiled clothes and water so that you can mix them together and flush it away. But in this case, we have a monolayer containing 3.23 times 10 to the minus 6 grams. 3.23 times 10 to the minus 6 grams of oleic acid. Everybody's heard of oleic acid. One of those essential fatty acids. And the oleic acid has an area of 20 square centimeters. So this mass on the surface of the water spreads out so that it occupies 20.0 square centimeters. Okay, so just turn this one on its side, and there you go. So your molecules, the hydrophobic end is pointing up, and on the surface of the water is the hydrophilic end. So what's the question? What is the thickness of the monolayer? That is the length of the molecule. What's this length right here? Okay, well, we know the area, and this is the height of a cylinder. Well, already got part of it drawn here. Let's say like that. Right? So this is the height. And this is the area. So the volume of the cylinder is this area times that height. Okay? So volume equals area times height. Do we know the volume? Not yet. I mean, we know the area. If we find the volume, then we can solve for the height. Okay? So how do we get the volume? Well, we've got this many grams. What else are we told? The density is 0.895 grams per milliliter. Density equals 0.895 grams per milliliter. There you go. That's equal to mass divided by volume. So we've got the mass here. So if we solve it for volume, that puts the mass 3.23 times 10 to the minus 6 grams over 0.895 grams per milliliter. Grams cancel, leave us with milliliters. Then we know the volume out of that calculation. Let's see, 0.23. Oops. 6 divided by 0.895. And that volume is 3.60939 times 10 to the minus 6 milliliters. Okay. I'm going to keep all of those decimals right now because all the calculations we're doing are multiply, divide. And I want to avoid rounding error. So I'm going to leave them all there and put them over here. But I'm going to solve for H first. H equals volume divided by area. So the volume is 3.60939 times 10 to the minus 6 milliliters. And the area, excuse me, did I do that right? Okay, area is square centimeters. Yeah, this is the same as cubic centimeters, right? If I don't do that, then I can't cancel units. And down here is 20.0 square centimeters. So we cancel 2 of those centimeters up here and it leaves us with 1. So that means our height is in centimeters. Okay. Now I'm going to round to 3 significant figures. 1.80 times 10 to the minus 7 centimeters. Now, our answers are given in centimeters, right? 1.80, 10 to the minus 7 centimeters is D. Okay. That was a complex problem. That's why I like to draw pictures. It helps me congeal. And as usual, I jumped all over the board. Sorry about that. My thought process doesn't keep me in an orderly fashion. Let's see, how about 57? The density of gasoline is at 20 degrees. When gasoline is added to water, that's simple. You guys get that one without even thinking. If you put something in water, and want to know, will it float or will it sink? What else do you need to know? Density. Density of water is approximately 1 gram per mil. So if the density of what you're putting in water is less than that, it'll float. If it's greater than that, it'll sink. And if it's exactly that, then, and it doesn't dissolve in water, then we would say it's neutral buoyancy. Okay, in this case, what do we have? 0.7 grams per mil, right? Gasoline. It's going to float on the surface, right? That's A. Let's see, 58. I don't want to eat into our lab too much. Okay, we just ran out of lecture time. I'm not even in chapter 2 yet. Piece of zinc with a mass of 12.14 grams is submerged in 46.3 milliliters of water in a graduated cylinder. The water level increases to 48 centimeters cubed, the correct value for density of the, okay. So this is one of those where you do calculate density. You're given the mass, that's not a problem. It's 12.14 grams. What we're looking for is volume. So assuming that piece of zinc is an irregular shape, then the best way to determine its volume is by difference. You submerge it in water and you note the difference in the change in volume. The change in volume went from 46.3, 6.3, let's see, answers cubic centimeter, up to 48.0 cubic centimeters. And that's our calculation. But this is 2 different rules, right? This is add, subtract, and that's multiply, divide. So we got to do the parentheses first. 46.3 subtracted is 0.7. 1.7. Yeah. So 1.7 and a 12.14 gives us only 2 significant figures. .1 grams per cubic centimeter. That would be B. Okay. And notice you've got one in there, 7.141. That's for the student that forgets to take significant figures into account. That has 4 significant figures. If you think that it's 4 because of that, then put it nicely, you'd be wrong. All right, let's see. 62, the boiling of water is a what kind of change? That's a physical change, right? Because the water still retains its identity. So it's a physical change. So it's A or B, but because what? Physical change because the water merely disappears? A better answer is because the gaseous water is chemically the same as the liquid water. All right. Okay, I put this one in here because these representations of atoms and molecules can be confusing. So we're looking at, let's see, 70 through 73 talks about those figures. So when we look at those figures, an individual dot or square or See, we got any others? Oh, okay. It represents separate atoms. And when we put two of them together, you got a molecule, or three of them together, whatever the case may be. So in the first, and notice also the distance between them and whether they're randomly arranged or regular crystal structure. Okay. So the first one is obviously a gas. Those atoms are really far apart, but it's a gaseous mixture of two different types of particles. So A is a gas mixture. Okay. B is what? B is a solid. It's regular arrangement of a pure element. It's a solid element. C is another gas, but this is a pure compound. Okay. This is a mixture of elements, just in case we need to know that. D looks like a liquid. It's randomly arranged of a liquid mixture of elements. And E. E is probably a gas. They're far enough apart. Let's see, we've got a compound and element. We've got a compound with two circles, a filled one and an empty one, and an element. So this one, I'm gonna call it a gas. I hope it's a gas. And it's a mixture of an element and a compound. Okay. Now let's see if we can answer those questions. Which best represents a homogeneous mixture of an element and a compound? That one. E. 71. Which best represents a gaseous compound? Let's see. A gas, pure compound. That's C. And which represents a solid element? Solid element should be B. And the last one, which best represents a heterogeneous mixture of two elements? Mixture of elements. Oh, heterogeneous mixture. That if that's a gas, it has to be homogeneous. Heterogeneous mixture of two elements is this one, D. Okay. 75. Let's see. Labs starts at yeah. Lab starts at 2. Does anybody need a break?
We allowed to just get up and go to that.
Oh, yeah, you can get up and go. I'll just keep talking and it's recorded. Yeah, if I didn't mention that at first, if nature calls, just pop up and go. Or if your phone rings, go out and answer it. Except during the test. Okay, so we got till 3:50. Right. I can go till 2:50. It gives about an hour to do the lab. Should be enough time. Introduce the lab, I should say. Do the lab, you can finish it at home. Okay, so 75. Yeah. Dig into my haversack. Get a brand new one. Which of the following has a different value on the moon compared to the Earth? Right. If we look at them in order, mass, it's the same everywhere. Right. Unless you're close to a black hole or you're traveling close to the speed of light. Otherwise, mass is the same everywhere. Weight is different. It depends on the gravitational field in which the mass is located. So if I weigh, let's say, I don't, but if I weighed, for ease of calculation, 180 pounds, right, on Earth, I weigh a sixth of that, right, 30 pounds on the moon. Time doesn't change, moles don't change. Weight's the only thing that's different on the moon. So that's the, okay. Chapter 2 yet? No, we got to do 80. And it's important, so we're going to have to do it. Which separation technique is based on differences in volatility of substances to be separated? Volatility changes with temperature, right? So at room temperature, if I open a bottle of water over there in the corner, you're not going to smell it. Well, that's not a good example because water doesn't have an odor. Let's say a bottle of pure ethanol, right? White lightning, crystal clear in the corner. Eventually, you might smell it over here. Take a while. But if in that same corner, I open a bottle of diethyl ether, you're going to smell it within minutes. So the volatility of the ether is much higher than it is than the ethanol, and much, much higher than it is for water. And the temperature determines volatility, but they kind of go in lockstep. So you increase the temperature, you make each of them more volatile. But the one that's more volatile to start with is going to evaporate first, quickest. So if we have a mixture of, let's say I have some corn mash that's been in the bin for, how long do they stay in there? A couple of weeks? Yeah. And we want to get the ethanol off of it, then we just have to heat it up because the ethanol is going to be more volatile. That's called distillation. We're going to distill that ethanol off of there, and it's based upon the differences in volatility. So distillation is the answer to this one. While we're here, what would be now these are all separation techniques based upon physical properties. How about filtration? That's purely particle size. Solvent extraction. And that's a little extreme. We didn't talk about solvent extraction. I did this from my master's degree, separating compounds in two solvents, a solvent mixture, in which you put your sample in there and you put the right combination of, and in my case, 3 ingredients, and you shake it up real hard in one of these separatory funnels, they call them. They're like this, like that, with a stopcock, a stopper there and a stopcock here, like that. And you put your sample in there, and the mixture is, the components have the ratios such a way that they will separate into layers. And the less dense layer is on the top, which is usually the more organic one. And if your compound is more organic, attracted to more organics, then it'll be up here. Right? So then once you get that extraction made, then you just drain this off. And when it gets down to the bottom, then you change your beaker and you pick up the layer that's got your sample in it, or your compound in it. So that's solvent extraction is based upon solubility differences. Paper chromatography is based upon, it's a combination of solubility and affinity for solids. So the paper is your solid, your samples are either attracted to your solid or not attracted to the solid. If they're attracted strongly to the solid, then they'll lag behind as the liquid moves up the solid. And the ones that are more attracted to the liquid will move faster, and eventually you get a separation. That's paper chromatography. Oh, finally, chapter 2. There, let's change this. Go. And number one. First people to attempt to explain why chemical changes occur were. Well, let's see. Alchemists, they're like Middle Ages. Metallurgists, the early metallurgists were more like cooks. They just knew what worked. Right? They didn't attempt to explain why. Physicians, no. And physicists, they didn't come along until modern times. Actually, the Greeks, the ancient Greeks were the first ones who tried to explain why things changed the way they did. And they got halfway there and then they got it wrong. Right? They discussed the atom. Right? Everything's made of this elementary particle, which is half right. And then, of course, like I said in the lecture, they had to do some wild mental gyrations to make that work. And that's typical with theories, right? When a theory fails, you have four options, right? You can either throw the theory out and start over again, which they didn't want to do, and most people don't want to do. Theories are kind of like their children. Second, you can modify the theory so that it takes your variations into account. Or you can restrict its use, right? Say it's not going to work outside these boundaries. Right? And that's where some theories end up, like Newton's classical mechanics, Newton's theories. And then, of course, the fourth one is one that you won't hear very often. You turn it into a religion. Then you just believe it. And everything you do tries to force it in a square peg in a round hole. And that's, yeah. Yeah, we're going to do like an introduction, but I haven't got there yet. I mentioned this before. Darwinism is one of those, turned it into a religion. Climate change is another religion. Okay. Number two. The first chemist to perform truly quantitative experiments was Robert Boyle, right? The Englishman. And his first experiments were on gases. And we're going to investigate that in a future chapter. I think it's chapter 5. Yeah, chapter 5. When we get to chapter 5, we'll talk about gases, and Boyle will come up. 3. Scientist who discovered the law of conservation of mass is also called the father of modern chemistry. Right? I'll give you a hint. He was French. Lavoisier. And he had the misfortune, as you recall, to be active during the French Revolution, or just prior to it. And, leftists are like that. They take your head when they can. And Lavoisier lost his head. I don't know what happened to his wife. I think she survived. 3. Wait a minute. I did 3. 4. There we go. 4. Which of the following pairs of compounds can be used to illustrate the law of multiple proportions? All right, multiple proportions, which was a law proposed by Dalton. Proposed by Dalton, said that if you have 2 or more chemicals that have they're binary in nature, in other words, you have 2 elements bound together in a compound, and you have homologous series. What I mean by that is they have the same elements, but the proportions, the mass proportions, are different, right? And the example I used was nitrogen and oxygen. So you hold one of them as unitary. So this is the same mass for each one. Say it's 10 grams here. 10 grams, 10 grams. That's not a good example. Let's see. Let's say 14 grams. There we go. 14 grams. This one's going to be 16 grams. This one's going to be 32 grams. This one's going to be 48 grams. That ratio, mass ratio. Remember, at this time, they didn't know about moles. They didn't know about individual atoms reacting with one another. All they knew is mass ratios. So this multiple proportions is mass, 14 grams to 16. And this one, this series, the difference between these are whole number multiples, right? This one's twice that one. This one's 3 times that one. That's what multiple proportions means. Okay. Let's see, we left out one, right? Definite proportions. What's definite proportions? That was Proust. It just says that no matter where the compound comes from, the ratio of elements in that compound by mass is always the same. And I use water as an example. I purify water from out of the tap, and I'm doing it right now in the lab, distilling water. That pure water is going to have a ratio of certain mass of hydrogen to oxygen, say 2 grams of hydrogen for 16 grams of oxygen. But if you make water from combusting hydrogen and oxygen, say in a rocket engine, you produce water that's exactly the same ratio, definite proportions. All right. 7. This takes a little mental acuity. A sample of chemical X is found to contain 5 grams of oxygen, 10 grams of carbon, 5 grams of oxygen, 10 grams of carbon, and nitrogen, 20 grams of nitrogen. Right? That's fixed. That mass ratio is the same for that compound no matter where it comes from. The law of definite proportions would predict that a 70-gram sample of X, so both of them are X, and a 70-gram sample would have how much of carbon? We're looking at this one. Well, what's the total here? 35. Right. So out of 35 grams, 10 of those grams are carbon. If we double the amount of the sample, we should also double the amount of carbon. So it should be 20 grams. E would be the best answer. Does that make sense? Okay. How about this one? Which of the following statements from Dalton's law are still true? I think that's what it said. In the modern atomic theory. Well, let's see. The first one, elements. Oh, no longer true. Excuse me. No longer true. So E says all these statements are true. So if all A, B, C, D are true, then E is correct. But if we find one that's not true, that's our answer. Elements are made up of tiny particles called atoms. Yeah, that's still true. Atoms are not created or destroyed in chemical reactions. Yep, that's true. All atoms of a given element are identical. Isotopes, they're not identical. They're chemically very, very similar. And we've been able to prove that even isotopes react just slightly different than other isotopes. It's probably due to their difference in mass. Atoms are indivisible in chemical reactions. Yeah, that's right. So we found our answer, C, right? Dalton didn't know about isotopes at that time. It was too early. Let's see. 11. The chemist credited for inventing a set of symbols for writing elements and a system for writing formulas of compounds and for discovering selenium, silicon, thorium. Okay, we didn't mention his name in class. I'm sure it's in your textbook. But the inventor of this system, which I'm very thankful for because the alternatives were nightmares, is Berzelius. He was a Swedish chemist. And he was, in fact, he did lots of stuff. We've got a beaker that's called a Berzelius beaker. It's about this big around, well, for 125 milliliter, 150 milliliters, about that big around and tall. They made them tall so that you could have reactions in the bottom and they wouldn't spew everywhere. Berzelius invented this system. Avogadro's hypothesis. Let's see. Avogadro's hypothesis says that if you have two gases where the volumes are equal, pressures are equal, temperatures are equal, the number of moles, the number of particles in each one is exactly the same. Now, which one of these statements fits that best? How about D? At the same temperature, pressure, equal volumes of different gases contain equal numbers of particles. That's it. That's Avogadro's law. Well, we call it a hypothesis. It's pretty much a law by now. 13. The first scientist to show that atoms emit any negative particles was J.J. Thomson. He used cathode ray tube. Negative particles. Okay, 14. Many classic experiments have given us indirect evidence of the nature of the atom. Which of the experiments listed below did not give the results described? Oh, so we got to look at each one of them. Okay, A. Rutherford's experiment proved the Thomson-Plum pudding model of the atom to be essentially correct. Just the opposite. He put it in its grave. Rutherford's gold foil experiment put a stake through the heart of the plum pudding model. Okay, how about, see if we got any wonky ones down there. All the above experiments gave results described? No. So we found our answer. You can be assured that B, C, and D are all correct. And the only reason I'm going fast on those is time. 15. The scientist whose alpha particle scattering experiment, oh, we talked about him already, concluded that the nucleus of an atom contained a dense center of positive charge, and that was Ernst Rutherford. And got a Nobel Prize for it also. Let's see, 16. Alpha particles beamed at thin metal foil may do what? Well, this is what Rutherford was basing his experiment upon. We know now that those particles will either pass directly through without changing direction, or they'll be slightly diverted by attraction to the electrons, or be reflected by direct contact with the nucleus. You know, A, B, and C. Easy answer. All three of those happen. I suspect that the detectors that Rutherford was using were photographic plates positioned in that big circle. He might have been done three-dimension. I haven't read any definitive stories about that. I just secondhand knowledge. But I'd like to read a biography of Rutherford and see what kind of person he was. Some of these people, I mean, we give them credit for making these massive discoveries, and in real life, some of them are real assholes. But we're thankful for what they did discover. And some of them are nice people. I think Einstein was a fairly pleasant person, as a general rule. More so as he got older and gave us those funny pictures. My favorite is one where he sticks his tongue out. Let's see, another one, he's riding a bicycle backwards. I guess when you get to be that age and you've done all your world-shaking theories and gotten your Nobel Prizes, you can do whatever you want to. 20. Let's see. Let's see. Which of the following atomic symbols is incorrect? Oh, okay. Those kind of questions, we got to run through them all. So we've got carbon with 6 and 14. Would that be correct? Well, let's see. Look at carbon. 6, yeah, has an atomic number of 6, 14. Could that be correct? Yeah, carbon 14 is radioactive, but it's true. So that was good. 3717. E for chlorine. Okay. Chlorine, 17 is correct. 37. Is it possible? Could we have an isotope with a mass number of 37? Yeah, they're not very abundant, but they're real. Phosphorus, 15 and 32. So phosphorus, there it is, 15, 32. Yeah, I'll go for that. How about D? K, 1939. Okay, 19 and 39. Okay, potassium's way over there on the other end. 19 is correct. 39, that's pretty good. So by process of elimination, E should be wrong. Nitrogen, 8 and 14. Okay. Uh-oh. Nitrogen, 7. 14 is good, but that's wrong. What would that element be if it were 8? Oxygen, yeah. Okay. Well, we found our answer. Here's the bad boy. Oh, 21. The element rhenium, and that's not one that I had you memorize. Right, the rhenium is right over here. Exists as 2 stable isotopes and 18 unstable isotopes. Rhenium 185 has in its nucleus, okay, rhenium 185 has in its nucleus so many protons and so many neutrons. So this is one where we're not given the atomic number. You have to go to the chart, look it up. So find rhenium at 75. So 75 protons. So it could be A, B, or D. And subtract the 2. 110 neutrons. So that's D. Let's see, 22. Which among the following represents a set of isotopes? All right, if you're going to have a set of isotopes, you've got to have the same number of protons. You can have different neutrons, but the same number of protons. So if we look down there, Roman numerals 1, 2, 3, 4, and 5, which ones have the same number of protons? We start at the top, 20 protons, 1 and 4 have the same number of protons and different neutrons. So 1 and 4 are isotopes. 21, 2, and 5 have the same number of protons and different neutrons. So what does that say? 2 and 5. 2 and 5. And that leaves 3. It's got nothing to go on. Right? It's all by itself. Has no isotopes in that list. So 1 and 4 and 2 and 5 is D. Okay. That should be our selection for isotopes. Let's see. How about 28? 8. Okay. A species with 12 protons and 10 electrons is. So I'm going to that's a placeholder. 10 electrons and 12 protons, which means it has a charge, right? Has an excess of 2 positives. That's 12 positives and 10. So we have a 2+ charge here. We have 12 protons. So we know that it is magnesium. So it's magnesium with a 2+ charge. C. Okay. Like solving a detective mystery. 29. All right. Number of protons, electrons, neutrons, and electrons in 1939 K plus. 1939 K plus. All right, in order of protons, neutrons, electrons. Protons, neutrons, electrons. Protons, obvious, that's 19. Neutrons would be 20, right? 19 from 39. How many electrons? Huh? Don't forget the charge.
So,
Yeah, he hesitatingly said. That's right. We're deficient by one negative, which gives us an excess of one positive. And that would be E. Okay, 33 coming up. Which of the following are incorrectly paired? All right. So this tests whether you know your symbols or not. And your groups, actually. So is strontium an alkaline earth? When we look over there, find strontium, it's in the second column. That's good. Strontium's an alkaline earth. Tantalum, Ta, is that a transition metal? Now let's find tantalum. Let's see, it's in the sixth period. Lanthanum, hafnium, tantalum, tungsten. Tantalum's right there. It's a transition metal. That's true. Fluorine. Everybody knows fluorine's a halogen. Hydrogen, is it a noble gas? I don't think so. Hydrogen is a element all by its lonesome. It doesn't fit anywhere. It's not a noble gas, right? The next one in the series is helium, but hydrogen's not. Ruthenium is a transition metal. You can find it there in the fifth period next to technetium and rhodium, palladium, silver in that group right there. Okay, so we found our answer. Go to the next one. 34. Which of the following is incorrectly paired? All right, now we're doing symbols and names. Is phosphorus PR? No, phosphorus is P only. What's PR? PR is down, there it is, right next to cerium and neodymium. I always get those mixed up. PR, is that promethium? Or is that praseodymium? I don't know. I haven't got those memorized. But it's not phosphorus. So we found the wrong one. The rest of them should be correct. Palladium, platinum, lead, potassium, those are all correct. Again, which one's not correct? Copper, is that Cu? Yep, Latin cuprum, Cu. Carbon, C, oh yeah. Cobalt, Co, oh yeah. Notice that's capital, small. Right? Remember what I said, if you do two capitals or two smalls, that's wrong. Calcium, Ca, yep. Cesium, Ce, no. Ce is cerium. Cs is cesium. It's an alkali metal toward the bottom. It's a big atom. In fact, there are some stable isotopes of cesium. 36. Which of these are incorrectly paired? Let's see. Antimony. SB? Yeah. Stilbium. That's Latin. Silicon. Si? Oh, yeah. Silver? Argentum. Ag. Argon. Ar? Yep. Astatine. As? Astatine is At. As is arsenic. So E is wrong. 37. Am I boring you guys? You got these down already? Got those flashcards going? All the following are characteristics of metals except. Let's see. A, good conductors of heat. Oh yeah. Malleable. Yep, you can shape them. ductile, you can stretch them in the thin wires. Often lustrous, if you polish them, yeah, they're lustrous. That's why they say often. Tend to gain electrons in chemical reactions. Nope. Metals tend to give up electrons in chemical reactions. All right, how about 41? You're given a compound with a formula MCl2. M is the metal, it's just a placeholder. You're told that the metal has 26 electrons. What's the identity of the metal? All right. We've got a metal with chlorine, like that. Okay. The metal ion has 26 electrons. 26 electrons. Well, if it's a metal and a non-metal, it's going to be an ionic compound. So this metal will have lost electrons. Okay. What's the normal charge for chlorine in an ionic compound? It's a halogen -1. So we know that this is 1 minus, so that's 2 minus here. That means this has to be a 2 plus to balance those two, correct? Okay. Now that we know it's a 2 plus charge and there are 26 electrons, we have 28 protons, right? In excess of 2 positives. So we look at 28 and we get to nickel. So nickel, it asks us what the element is. Yeah. Identify the metal. So we just say nickel. It has a 2 plus charge in that compound, but the metal itself is nickel. E. How about 45? Question, how many oxygen atoms are there in one formula unit of calcium phosphate? Calcium phosphate. This is, all right, is this a type 1, type 2, or type 3? For naming purposes. Type 1. The metal has only one possible charge, 2 plus. It's an alkaline earth. So this is a type 1 compound with a polyatomic ion. Okay. But that's not the question. The question is, how many oxygen atoms are there? Well, this parentheses applies to that whole unit. So 4 times 2 is 8. There are 8 oxygens in that molecule. In the formula. 8 oxygens in that formula unit. Okay. And we got to name compounds here. 47. All right. 47. The correct name for FeO. We got to decide. Type 1, 2, or 3. Well, it's not 3 because there's a metal and non-metal. So it's either 1 or 2. 2? Because iron is a transition metal, which means except for that, let's see, this one, and this one, they all have variable charge. So that means iron has a variable charge. So we have to write iron, oxide. Then we have to determine what's the charge on iron. Well, oxygen's a chalcogen, and they're all 2 minus when they're in ionic compounds. That means this one has to be a 2 plus. There's your name, which should be B. Correct name of Ca2 plus. Ca2 plus. All right. Again, calcium is an alkaline earth. It can only have one charge. So do we have to say what the charge is? No. We just say it's calcium ion. Period. That's 2 plus. C, calcium ion. How about V3 plus? What's V? Vanadium. V3 plus. Vanadium can have multiple charges, right? It's like calcium, scandium, titanium, vanadium. It can have multiple charges. So when we say this, we say vanadium 3 ion. Okay. All right, 51. Let's make some room here. What's the subscript of barium in the following in the formula barium sulfate? Barium sulfate. A polyatomic ion with a 2- charge, right? How about barium? Barium is an alkaline earth. It's always 2+. That's it. So the subscript is 1. Right? If we don't write a number, it's automatically 1. If it were 0, we wouldn't write it there, right? That's because E is 0. That doesn't make any sense. Sometimes when we get down to E's, we just kind of make stuff up, pull it out of the blue. We run out of ideas. 53. Okay, 53. Formula of sodium dihydrogen phosphate. Sodium dihydrogen phosphate is a polyatomic ion. If you look it up in that list, dihydrogen phosphate. Phosphate has a 3- charge. Monohydrogen phosphate has a 2- charge. Dihydrogen has a 1- charge only. That's it. Because the hydrogens have neutralized the others. So, and sodium in an ionic compound is +1, so that's it. Just NaH2PO4. A. Okay, we got a bunch of other practice ones in there. All the following are in aqueous solution. Which is the incorrect name? Okay, if it's an aqueous solution and it starts with a hydrogen in the name, then we have to name it with the acid naming convention. Okay, we're looking for the one incorrectly named. All right, so if we're going to name H2SO4, we start with, all right, if we have oxygen, we don't say hydro, correct? We go straight to the anion part of the molecule. And we say, all right, that's sulfate. And in the naming conventions, and just assume all of these are aqueous solution. This is 8 becomes ic. Sulfuric acid. Is that correct? Yep. Okay, H2CO3. H2CO3. Again, no hydro. This is carbonate. H become X, so it's carbonic acid. I used to think, first time I heard that, carbonic acid. I don't want to go near that. That's in every pop bottle you ever drink. Carbonic acid, it's a weak acid, so it's not going to hurt you. C, at least at those concentrations it won't. H3PO4. Again, no hydro. So phosphate, right? These are all polyatomic ions. That one, that one, that one. 8 becomes ic, so it's phosphoric acid. Is that what it says? Yeah. HCN. HCN. Okay. No oxygen, so we start with hydro. This is the cyanide polyatomic ion. We start with hydro, and I becomes ic, hydrocyanic acid. That one's wrong. And E is the last one. HCl is hydrochloric acid. Okay, so we found the bad one, D. And next is 59. I have to,
Get a fresh marker.
these things don't last very long. $59. Which of the following names is correct? All right, sulfide. Okay, sulfide's correct. Ammonium chloride. Yeah, ammonium is a polyatomic ion. You don't have to change the name because polyatomic ions are fixed in name as well as charge. Ammonium chloride, that's correct. That would be considered a type 1 because ammonium has a fixed charge. Acetic acid. C2H3O2 is the acetate ion. H become ic. And we don't say hydro in this case because there's oxygen. So we say acetic, acetate, acetic acid. That's correct. Right? It can come in various concentrations. 5% is vinegar. Glacial is 100%, and will, even though it's a weak acid, if it's glacial, it'll eat your hand off. Barium oxide, is that correct? Barium is an alkaline earth, 2+ charge, oxide, 2- charge, 1 and 1. That's correct. Yeah, barium oxide. They're all correct. Okay. Anybody have trouble with this table? Know how to work that table? We didn't do one of those in class, did we? Okay. All right, we'll do 61 and skip 62 because it's the same type of approach. All right, 61. And we've got columns labeled symbol. Let's see, protons, neutrons, oops, capital, should be a little, and electrons, and net charge. Okay. Let's see, we have 1, 2, 3, 4. Let's do one in the middle and then split the difference. Here we go. All right, what are we given first? We're given 206 dB lead. And we're given here, given 31, 38, and 3+. And we're given 52, 75, 54. And here we're given Mn to plus 30 and 2+. Okay. Now we want to fill in the missing blanks. I got a colored one in here somewhere. Let's try blue. Okay. Number of protons for lead. Just look it up. 82. Number of neutrons, 82 subtracted from 206. See, 4. Got a loose thread. Let's see, 4, 2, and 1. And then number of electrons is neutral. Number of electrons exactly the same as the protons. And the charge is 0. Okay. Symbol, 31 protons. Gallium. Okay. Let's see. If we want to be, well, this one doesn't have a mass number, so we don't have to put it for that one either. But there's a charge, right? 3+. There you go. Number of electrons. Number of electrons, let's see. Well, we've got 31 positives, which is 3 excess from the number of electrons. So we should have 28 electrons. Okay. This one, 52 protons. Tellurium. Does it have a charge? Well, we have to see. Let's see. $54 electrons, has 2 extra electrons, 2 minus. We could put a value in here. That's 69. Yeah, and this one would be 120, let's see, 97. No, 127. This one has a 2, it's already given. Manganese. 25 protons with a 2+ charge means 23 electrons. Okay. That's how it's done. Actually, simple math. I'll let you do the following table. And then we'll go on down to symbols. Uh, 63. Oops. Go back to the black one. Okay, silver, Ag, right? Calcium, Ca. Iodine, I. Copper, cuprum, Cu. If you put Co in there, you're claiming it's cobalt. Phosphorus, P, capital P. All right, next one may be a little more difficult. FeSO4 is iron. Let's see, this is 64. Is, yeah, iron, type 2 compound with a polyatomic ion, sulfate, which is a 2- charge. This has to be a 2+. So we put like that, like that. You don't have to have these in there. I just did that for calculation purposes. NaC2H3O2. That's sodium. And it's a fixed charge, so we don't need any Roman numerals. And then the polyatomic is acetate. How about KNO2? Potassium is a fixed charge, so that's a type 1. And what's that NO2? NO3 is nitrate, NO2 is nitrite, and they have the same charge. That's what they put in some foods. Actually, they use sodium nitrite. It's cheaper as a preservative. Bacteria don't like it, so they put it in our foods. You can go without it. I mean, you get foods that are like meats that are uncured meat, won't have any nitrates or nitrites in it. I don't know, it just has an off flavor to me. I like my meats poisoned. CaOH2. So calcium has a fixed charge, but we've got O2, OH, which is a minus charge, -1 polyatomic hydroxide. But all we have to do is balance the charges because calcium is a fixed charge. So calcium hydroxide is the only name you need to give you it's gone blank. It's not redundant. In other words, we don't put a charge in there. That would be redundant. Unambiguous. There it is. It's unambiguous. Right? You can go backwards from this to the formula. If you know what you're doing and know the rules, no problem. NiCO3. That's nickel, which is transition metal. So we need to know the charge. And carbonate. So what's the charge on carbonate? Polyatomic ion, 2-. So nickel has to be that because there's only one of them. One to balance the other. All right. Nitrate ion, that one's not right. That's a mistake. Nitrate should be NO subscript 3. Let's see if I can remember how to do this. Nope. It's not it. No. I should be able to bring up the edit panel. I thought it was, well, maybe it's not the this symbol. Maybe it's Alt E. Nope. Control E. Nope. Oh, I can't remember. To put in the subscript. Should have a subscript there of 3. It's not going to let me modify it. Oh, it's there. It's just not visible. Okay, that's a problem with the program. Sorry. It should be nitrate ion should be, well, let me erase these. Start stepping on each other's toes. 65. So the nitrate ion, you need to look that one up. You know, 3 minus. Aluminum oxide. The aluminum is a 3+ charge. Oxygen is a 2- charge. Now, how do you balance an odd and an even? I go back to math, cross multiply. Bring the 2 over here and the 3 over there. 2 times 3+ is 6+, 3 times 2- is 6-. They balance. Ammonium ion. Ammonium is polyatomic ion with a 1+ charge. D, perchloric acid. All right. Remember that list of chlorine, oxygen homologs? I did the chlorate, then I did the chlorite, hypochlorite, and then I went on top and did the perchlorate. The perchlorate is ClO4-. If you add a hydrogen on the front, that takes away the negative and make an acid out of it. That's perchloric acid. And then the last one, copper 2 bromide. So copper has a 2+ charge and bromine has a 1- charge. So that means we need 2 bromines, CuBr2. Okay. Let's see, are we getting close to the end? Okay, we've got a bunch of compounds to name. Let's take it this way. Anybody have trouble with those? Remember how your flow chart in your head for reasoning naming compounds. If it's a nonmetal and a nonmetal in the binary compound, you go to type 3 automatically. So then you just say how many of each. Example of that is 70, carbon tetrachloride. Or 74, dinitrogen trioxide. Okay, that's all you have to do for type 3s. If it's a metal and a nonmetal, then you got to break a tie between type 1 and type 2. If the metal is a fixed charge that comes from alkaline metals, alkaline earths, aluminum, gallium, indium, and boron, if it's in a, nah, I wouldn't say boron, aluminum, gallium, indium, 3+. Then the nonmetals would be halogens -1, chalcogens -2, nitrogens -3. Okay. If that's the case, if you have a fixed charge of metal, then use the type 1, and you don't have to say what the charge is. Like silver chloride. Silver is one of those in the transition metals that's a fixed charge. Silver, cadmium, zinc. Silver is a +1, cadmium and zinc are +2. Right. that right? Yeah. Okay, I'm right. Or calcium sulfate. And then the polyatomics are fixed charge, always. And they're fixed name also. Okay. There's another one going the other direction. Thiosulfate. How do you tell if you've got a polyatomic ion that has to be named? More often than not, they're going to be the second part of the name. They're going to be the anion side. And they're not going to be readily identifiable as elements. Like, I don't know, chloride, sulfide, nitride. Right? They're going to be odd names. Thiosulfate, you're not going to find anything that starts with an element on the periodic table that gives you thiosulfate. That's a polyatomic ion, so you need to look that one up. S2O3 2- would be the thiosulfate. Let's see, hydroxide. Hydroxide is a polyatomic. Acids, right? Acids, if it's sulfurous acid, you work backwards. Eights become X, ites become us's. So sulfurous would start with sulfite, SO3. So you go to your polyatomic ions, SO3 2-, and then you add however many hydrogens you need with a +1 each. Okay, H2SO3. Acetic acid, I wrote two different ways here. Your book is probably going to write it HC2H3O2. And I learned it this way. It gives you a little more information about the structure. Because when you draw out the structure of this molecule, you have 3 hydrogens here attached to that carbon, and another carbon, and then a double bonded oxygen and an OH. That is your acidic hydrogen right there. This is the carboxylic acid. It tells you a little more about the acid than the molecular formula does. But you can, either way, it's fine. If it's multiple choice, you probably won't see the CH3COOH. Phosphorus trichloride, that's a metal, it's a non-metal, right? So that's easy. PCl3. Okay, there's definite proportions. We did that one already. Multiple proportions, we've talked about that already. Which one of these doesn't have a symbol from the Latin? Iron is Fe, right? That's got to be Latin. Copper is Cu. Sodium is Na, natrum. Potassium is kalium with a K. And titanium is Ti. That's the one. Titanium can be related to the English word. Which of the following ions is not likely to form from the appropriate atom? All right. Maybe I better do this one on the board. Okay. We've got this one, magnesium, titanium, and sodium. Okay. Let's eliminate these. Sodium is an alkali metal. They're always +1. So we can throw that one out. Magnesium is an alkaline earth. They're always 2+. Arsenic, where does arsenic come from? It's under phosphorus. The nicogens are always 3- when they're in ionic compounds. So we throw that one out. So we got to decide between titanium and carbon. Not likely to form from the appropriate atoms. Okay, titanium is one of those transition metals. It's likely to have a positive charge and very likely to have a +4 charge. The reason I say that is it's 4 positions moved over from calcium, calcium +1, then +2, +3 possible, +4 possible for titanium. More than likely. Now, later on, we're going to find out why that works. So I throw that one out, and by process of elimination, 4+ is unlikely for carbon. It's not unheard of, but it's unlikely. If we put carbon in the second position, then we say it's carbide. And you can form a whole host of different carbides, and they're all ionic compounds, and they're very, very hard. Like aluminum carbide is a good one. Aluminum carbide. I'm trying to go with the cheaper ones. Do we have an iron carbide? I don't think so. Potassium carbide, maybe. They use them in sanding paper, the carbides, because they're so hard. But then they're not usually 4+. They can be, but not usually. So that's process of elimination. We're left with this one that is the least likely. How did they word that? Not likely to form. Okay. So we're qualifying our statement. We're not saying absolutely, but it's not likely. Okay. Let's see. How many protons, neutrons, electron in the anion of iodine? So what charge would it have? It would have to be a negative because it's an anion. It's a halogen. It has to be -1. So you start with -1, and then you work back through your protons, neutrons, and electrons, just like we did before. I'm trying to hurry up. I'm going to leave that one to you, 94 also. Which of the following compounds is incorrectly named? I'm going to have to leave that one to you also. Unless you have a specific question. Did anything come to mind while I was rambling up here? Or do you feel fairly comfortable? Okay. I hope you got your elements memorized. Or you're well on the way. Let's put it that way. Well on the way. Do those extra credits, that'll help. Fill out that periodic table, that'll help. That's extra credit. Name your compounds, that's extra credit. Work those crossword puzzles and gain some points there. Those are due on the exam day. Okay.